In this video, we're going to learn about how we can use vectors, in particular, something called a normal vector, to write an equation of a plane. So recall we've looked at planes before in a previous section of our course. Well, now we're going to learn a different way to write that same equation of a plane. All right, so let's get started by first defining a normal vector. So a normal vector of a plane is just any vector, let's call it n, that is perpendicular to the plane. So if we have our plane here in this image, say P naught is a point on our plane, then a normal vector of the plane would look like this, sticking out perpendicularly from the plane. So now our job is to try to create an equation or a formula for any other point P on the plane. So I have here, let P equal X, Y, Z. So what we want to do is create a formula with that X, Y, and Z so we know which points lie on this plane. Okay, so to do that, we can make the following observation. So notice that any point on our plane at P, if we look at the vector from P naught to P, this vector is going to be orthogonal to n, or it'll meet n in a 90-degree or right angle. So that would mean that the dot product between the vector n and the vector P naught P is going to be 0. So I'm going to make that note just so we can really let that sink in. So note or observation, n dot P naught P is equal to 0 for any P on the plane. So this is going to be the way that we create that formula. All right, so to do that, we're going to look at the dot product kind of for a general P. So let's look at what that looks like together. So let's let n vector be the vector, say, that's determined by coordinates ai plus bi, plus bj rather, plus ck. So n is just our normal vector, and I want to keep this discussion very general. We're not looking at a particular plane. So that's why I'm using constants a, b, and c as our components. So now how do we describe the vector P naught P? So we know that the vector P naught P starts at the point x naught, y naught, z naught, and goes to the point x, y, z. So to create that vector, what we do is we just subtract corresponding components, and that will be the resulting component. Okay, so what does that look like? So we could start with P, subtract P naught. And that's how we always write these vectors in any dimension. So if we want to write the vector between 2 points, P and P naught, we start with P and subtract out P naught. This is pretty obvious when we're looking at 1 dimension or 2 dimensions. In 3 dimensions, it just continues to work the same way. All right, so that would look like x minus x naught I plus y minus y naught j plus z minus z naught k. And so again, we know that n dotted with P naught P vector is equal to 0. So let's go ahead and write out what that dot product looks like using these two forms of our vectors. So for that dot product, what we're going to do is just multiply components and add together. So we first get a times x minus x naught I plus, and we'll look at b times y minus y naught and that is our j component. And then finally, we look at multiplying our k components. So we get c times z minus z naught, and that is in the k direction. So this dot product is equal to 0. So this, what we just wrote down here, is another way of writing the equation of a line. plane, equation of a plane. I'll write that down just so it's clear in our notes. So here is an equation for the plane. And for this plane in particular, we have with point x naught, y naught, z naught, and normal vector n. So one thing I want us to observe about this equation is that the coefficients here, a, b, and c, are those components in our normal vector. So oftentimes we can read off a normal vector based on how that equation is presented to us. All right, so let's wrap things up with just summarizing the various ways of writing the equation for a plane that we've seen. All right, so first, if n is the vector ai plus bj plus ck is a normal vector to a plane, and x naught, y naught, z naught is a point on the plane, then the equation for the plane is given by that equation we just found. So that is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So notice this is a perfectly acceptable equation. We only have x, y, and z as our open variables. The a, the x naught, the b, y naught, c, z naught, those are all going to be some fixed numbers. So we see here that this does indeed give us an equation of a surface in 3 dimensions. All right, now let's recall the other way that we've seen how to write an equation of a line or plane. So we saw again in section 12.4 that if m is the slope of the plane in the x direction and n is the slope of the plane in the y direction, and we have a point x naught, y naught, z naught on our plane, then the equation for the plane is given by z equals z naught plus m times x minus x naught plus n times y minus y naught. All right, so I just want to end this video with a few important notes on the equation of planes. So one thing, this equation up here that we just met in this video, often we rearrange the terms. So we multiply out the a into each term, the b, the c, and then we gather the constants in the end. That is what is called standard form. So I'm going to just write that out. So by, we'll say, rearranging the terms in one above, we can rewrite the equation of a plane in what's called standard form. So when we do that, what happens is we'll have that a on the x, the b on the y, the c on the z, and then again, we'll have these constants. We'll subtract an ax naught, we'll subtract a by naught, and a cy naught, cz naught. And so essentially what that would look like is ax plus by plus cz equals some constant. We could even compute what that constant is. It should be something like ax naught plus by naught plus cz naught. And again, that's just by distributing this a, b, and c into all the terms, and then adding our constants over. All right, so that's kind of our first note. Our second note is just to recall what information we need for finding out the equation of these formulas. So for one, what do we need? We need a normal vector, n, and point on our plane. Well, for 2, what do we need? Well, we still need a point on our plane. Let's again, call it x naught, y naught, z naught. And we need the slopes in x and y direction. So then you might be asking yourself, well, which of these 2 equations or formulas do I use to write my equation of a line? Well, it depends on the situation and what information you're given. So if you're given information about a normal vector and a point, then we're going to use the first graph or the first equation. But if instead we're given something like a table of values, where from that table we can determine the slopes in the x and y direction, then we'll want to use the second equation.